Now we will address the issues around thermodynamically limited reactions, and we are going to learn how to design the reactors if the reactor is operating under adiabatic conditions, and I will also discuss why the reactor has to operate under adiabatic conditions. Now let's first see the conversion versus temperature diagram, equilibrium conversion versus temperature diagram for an exothermic reaction. This is a typical general behavior of an exothermic reaction. As the temperature increases, the equilibrium conversion decreases. And of course, it is, if we are desiring to have higher conversions, it is better to operate this reactor at lower temperatures, where we can have very high conversions, very high equilibrium conversions. And also, we have to remember that the thermodynamics impose an irremovable barrier on how to the extent of conversion that we might have in this reactor. In other words, we cannot have conversions that are higher than the corresponding thermodynamic equilibrium conversion. So if I can operate this reactor at this lower temperature, then I can have close to 100% conversions and everything is good. The problem is that when I operate at these low temperatures, that I have very low rates, that it takes forever for this reaction to go to completion. The rates are very slow, and the reactor volumes demanded by those small rates are going to be very large. Now what should I do? Go to higher temperatures. But at those higher temperatures, then I have low conversions. So now, how can I compromise? The compromise comes through a balance between lower conversions, lower temperatures, and using the reaction's heat to increase the temperature, and as a result, go to faster rates, but we're going to be limited by the equilibrium conversions. Now let us start from a T0 domain where our reactor is fed at a lower temperature. The reactor is operating under adiabatic conditions, and our energy balance dictates a linear relationship between conversion and temperature, right? The linear relationship between conversion and temperature goes like this. So I have started at this temperature with zero conversion. I let my reaction run its course within the reactor. Although the energy balance curve can be extrapolated, nature dictates that my rates are zero at the point of equilibrium. So I cannot go beyond there. There is no point of moving further. There's no point of moving very close to the equilibrium point, because as we approach the equilibrium, our rates diminish faster, right? And we are going to find an envelope where we can have a reasonable conversion, a reasonable rate. We're going to stop here, find a way to cool the contents, and then proceed. Okay, so how am I going to cool the contents? I can put a heat exchanger. With a heat exchanger, I move horizontally, that my conversion remains the same, my temperature decreases. Or I can add some cold feed. It's cold, fresh feed. If I add cold, fresh feed, that cold, fresh feed just changes the conversion. I'm at a lesser conversion and at a lower temperature. Let's proceed with the heat exchanger scenario here. Take this, run the reactor one more time, use a heat exchanger, cool the content, run the reactor, and depending upon the physics and chemistry of your system, you may end up having very, very high conversions. All right, but the reality of the situation, which I will give two examples from the real industrial chemical manufacturing. One of them is ammonia synthesis, the other one is methanol synthesis. And both of these reactions are mildly exothermic. Being mildly exothermic means that our equilibrium curve starts to move downwards at moderate temperatures, moderate enough for our chemical conversion purposes, that we have to resort to solutions such as these. Okay? Ammonia synthesis or methanol synthesis are our examples. Now, the qualitative examples are going to be discussed in the video. When it comes to the quantitative analysis, we will work through the chug and plug details in class. Now, let me take this diagram and show it in a flowchart of a packed bed reactor. Okay, I have a packed bed reactor, my hypothetical packed bed. My feed enters this packed bed. My slightly converted, let me start this 0 and label this 1, 2, 3, 4, and 5. So this is my point 0, T0, Ca0. This is my point 1, T1, Ca1. I put this stream in a heat exchanger. I'm now at T2, which is less than T1. My objective is to decrease the temperature, but my concentration is the same. I send this to a second reactor. This is T3, Ca2, another heat exchanger. Now here I'm T4 and Ca4. No, Ca2. Okay. And send it to another reactor. Then I have T5 and Ca3. Whether I cool the reactor effluent or not depends upon my overall optimization of this whole process. Now, the fact is that despite my hard work of trying to keep temperatures low and conversions high, that the real situation gives me in a typical ammonia synthesis reactor, close to 15% conversion at the exit of the third stage. This is not acceptable, right? We cannot throw away 85% of our valuable reactant. We have spent huge amount of money to purify nitrogen, to generate hydrogen, and now we cannot throw away the unconverted part. What are we going to do? We're going to put a separation unit where we are going to have liquid, hopefully liquid ammonia. We're going to condense and separate ammonia. Then we are going to take the gas part all the way back to the feed. Now this stream is called the recycle. Of course, there will be a little bit of ammonia laden onto the recycle stream, and that enters into our first reactor, and hence at the inlet of our first reactor, even at the inlet of our first reactor, our conversion is going to be minute but non-zero. So we are going to determine how much we are going to recycle. If we have impurities in our feed stream, and we do, how much we are going to purge, and what will be the sizes of these reactors. They don't have to be equal. All right, but there's one problem. Ammonia synthesis reaction is a variable volume reaction. What do I mean by that? Methanol synthesis is a variable volume reaction also. Let us write the reaction stoichiometry. I started with 4 moles of reactants, and I ended up having 2 moles of product. My delta is -2. Net stoichiometric coefficient is -2. What's happening? My reactants, my system, as it reacts, the volume shrinks. Okay? So it's a flow reactor. This is a flow reactor. In order to keep the pressure constant, and it is important to keep the pressure constant, because as we will see when we are chugging and plugging the numbers, we will see that the equilibrium curve is also a very strong function of the overall pressure. So we would like to benefit from the high pressure in order to push this reaction forward by using the Le Chatelier principle. High pressures favor the product side. So we would like not to lose that high pressure. So what we are going to do is we are going to shrink the size of the reactor. Or perhaps it's better that we discuss the concept of a radial flow reactor. Now, what is this? This is an axial flow reactor. Things are moving in the axial direction. Now, let us take a circular cross-section, Let us take a donut-shaped reactor, all right? A donut-shaped catalyst packing. Now, if I feed my reactants from the surroundings to this donut-shaped domain. As they move through the packing, you'll see that the volume is going to decrease. That the reactor volume is going to look to the hydrodynamics, to the gas phase reactant as if the volume is shrinking. And hence, we will be able to maintain our pressures, and we won't have to deal with, with this design, we won't have to deal with large pressure drops due to the packing. So, we have a radial flow reactor. Of course, this outer side is the inlet, and inner side is the effluent of this radial flow reactor. And of course, when you take this donut shape geometry, right? You arrange your flow in such a way that it comes through the circumference, it leaves through the center, it goes through a heat exchanger, and goes to the next stage. All right? And of course, how you arrange your flow through this reactor may mean that may mean a lot of in terms of economics, because under those systems where we have a lot of high pressure domains, managing the flow and pressures is going to determine how well you manage your process economy. The process economy for this problem depends highly on the compressor duty, both in the recycle stream and also here. Of course, what I drove there is a pump, it's not a compressor, so let me just draw a true symbol for a compressor. All right. And of course, we provide significant amount of shaft work for increasing the pressure of the recycled gas in order to match the pressure of the incoming gas. So in order to design this radial flow reactor, we have to choose a non-trivial methodologies. It's not trivial to estimate the hydrodynamics in the radial direction. It is not also trivial to estimate the temperature and concentration distributions. So once we do that for each stage, then we have a good estimate on how much catalyst we need, how thick should be the donut zone for catalyst packing, how much heat I should remove, what should be my low temperature, because the lower the temperature, the worse the rates. I would like to remain closer to the high temperature domain, but not too close, right? These are all parameters that we have to optimize in order to be able to have better economy at the end, better economy of manufacturing our desired product. Well, there could be certain strategies that we might use for things like we have started to hear as process intensification. What is a process intensification? Is combining more than one process unit in one process unit in order to save time, energy, process unit investment, and also in order to improve the process economy. Now, as far as ammonia synthesis is concerned, a clever design is now being debated, and that clever design uses an absorbent within the reactor. In other words, my catalyst bed does not only contain the catalyst to convert nitrogen and hydrogen to ammonia, but also I have a second component in my solids where I have absorbed let's imagine that this is our packed bed reactor, right? We have fed nitrogen and hydrogen. Here in this reactor I have my catalyst, but in addition I have an absorbent. Okay, ammonia is a basic molecule, so if I have a sufficiently acidic solid in the bed, ammonia will make a complex with that solid. So what did I do? I removed ammonia from the reaction environment. When I remove ammonia from the reaction environment, it is physically in the reactor, but it is away from the reaction environment. Where is the reaction environment? It is the surface of the catalyst. It's an atomic molecular layers that we are talking about. That I removed ammonia from the surface of the catalyst, and my surface is now free. My Le Chatelier principle pushes the reaction forward until when? Until I finish all the nitrogen and hydrogen, okay? Provided that I have sufficient absorbent within the reactor bed. Then I shut off the gas flow, reactant gas flow, and then I turn on the product valve. I can evacuate by vacuuming, by evacuation. You can just let the system discharge itself because of the high temperatures. I might generate a vent zone at lower pressure where my reactor contents can be evacuated. Now this is a simpler and easier to operate design, but it is affordable on small scale. When you scale up, still the multi-stage recycle reactor is more profitable because we have learned so much for ammonia synthesis over the years since Fritz Haber first came up with the catalyst, and Carl Bosch has designed this multi-stage system. Eventually they were awarded the Nobel Prize for their contributions.